I've talked about how when you have two sets of ripples generated by two separate rods pushing in and out of the water, how the two sets of ripples would interfere with each other, and how it would be possible, say at some particular point, some distance away, for the ripples meeting at that point to either add together to give a big oscillation with a big amplitude, or for them to cancel each other if the peak always happens to meet the trough at that point. Now let me explore this a little bit further using a slightly different setup. Now what I'm going to do is to think about this. As I mentioned, in order for, say, for this to happen, in order that I can have a point that would always have where the amplitudes would always, the displacements would always add in the same direction and give a big amplitude, or where the displacement would always cancel. In order that these points stay the same, I must move the two rods up and down together. Now, but what happens if I get tired? What happens if my left hand gets more tired than my right hand, and my left hand slow down a bit? Then I'm going to mess up this pattern, because if my left hand is a bit slower to generate a peak, then that peak might not get here in time to meet the trough, and I might start getting a different pattern. So what I want to do now is to think of a way to prevent this from happening, a way that that will, even if my left or right hand gets tired, right, I can still get a stable pattern. Now, how is that even possible? Now, here's what I'll do. Let me remove the two rods, a long ruler here, and I would move this ruler up and down, just up and down into the water to generate ripples that are nearly straight lines that travel outwards. And I'm going to put here, I'm going to put some straight lines, straight pieces of maybe wood down here to block some part of this wave. Okay. Leaving just the two gaps for the wave fronts to come through. So this piece of ruler would generate ripples that are straight lines and that start traveling outwards, and those parts that reach the gap would come through. Okay, and they would spread out because the gaps are quite small, so it will have diffraction as it goes through the gap. It will start bending around the corner and spread out. Okay, so likewise for that other gap. So as they spread out, they will meet. Alright, the two sets of ripples will meet. So, in other words, I've just from one set of straight line ripples, if you like, I've used two gaps to separate that wavefront, that wave, into two separate sets of waves. I have divided the two wavefronts. I've divided a single wave into two waves. Okay, I've split it up. And these two waves is then guaranteed to be coherent, even if my arm gets tired pushing it up and down. Because let's say I got tired and I skipped a period. All right. So what happens is this: the ripple here might just stop for half a second. All right. So I would have a missing peak, but the next peak will come after my arm has rested for a little bit and start going up and down again. So it will start generating the next peak, and the next peak that comes would again be coherent. Okay, so although my arm might be tired and I might slow down a little bit, whatever comes out here will always be coherent, meaning that when a peak come out here, a peak will come out here. When nothing come out here, nothing will come up here. So in that sense, it can always be coherent. So in this way, by splitting a single wavefront into two, I have solved the problem, that generating the two waves separately might have. Right? Because if I generate the two waves separately, there's always a possibility that I'm tired or there's some other error, and then they won't be coherent. But in this case, by splitting up a single wavefront into two, they will always be coherent. Now what I want to do next is, let me just write this down. So it is a way to ensure that the two waves are coherent. Split a single wave front into two. So this ensures that the two separate waves are coherent. This gives two coherent waves. Okay. Now the next thing I want to look at is I want to look at the pattern of the interference along maybe some distance away, maybe along here. Okay, maybe along here. Now, as I've described previously, I know that if I'm at a position where that is at the same distance from the two the two sources of the wave, I can think of these two gaps now as my new sources of the wave. So if I'm at a point that is at the same distance from those two gaps, then the peak coming out from this gap and from that other gap, the peak that comes out at the same time, will always meet here. And likewise, a trough coming out at the same time will always meet here. All right, it will spread out, of course, but the particular wave that comes in this direction will always have peak meeting the peak or trough meeting the trough. So I will end up with a big oscillation here. So that's what I would expect. And down here, I would expect a big oscillation. And that's when the distances are the same. Now, if I imagine moving away from this center position, right, as I move away, the distance changes, right? The distance from the two gaps, the distances from two gaps change. And as I move away, it could be that maybe this distance and that distance are such that there's a difference of, say, half a wavelength. Okay, so in that case, if this distance, let me me draw say a straight line to here and a straight line to there. Okay, now I would let me call this point, let me call this A, let me call this B, and let me call this P. So I have these two distances, right? I have AP and I have BP. Now, if the difference between these two is, let's say, half a wavelength, right? As I move away, let's say the difference is half a wavelength. Then, as described in the previous session, we know that a peak from A would always meet a trough from B because they're off by half a wavelength. Or a trough from A would meet a peak from B. And therefore, they would always cancel each other. They will always cancel each other. So there's no oscillation here at all. Now, if I move a bit further away still, okay, to let's say here, I may reach another point, okay, where the difference between the two paths, because as I move further away, this distance increase and that distance might decrease, or it might not increase so much. Right? This distance might increase more. So I would reach another point, for example, where say the difference instead of half wavelength is maybe one wavelength instead. Right? If I'm there, then there'll be a difference of exactly one wavelength, which means that the peak from here, from A, would again meet the peak from B. So if I'm at such a position, I would expect once again a big oscillation. So as I move along this line, I would expect to see this repeating, the change from a big oscillation to no oscillation, to a big oscillation, to no oscillation, and so on. So maybe a big oscillation there, a big oscillation there, and then in between there'll be no oscillation. There's nothing here, no oscillation there. That's where peak meets trough and they cancel. Now what I like to do is to write down the condition for this to happen in terms of these two, of those two paths. Right? We have already seen that when the difference between those two paths is either 0, it's equidistance, or one wavelength or two wavelength, meaning a multiple of a wavelength, we have this situation where peak meets peak and trough meets trough. Okay. So let me try writing this down. So when the path difference, I'll call this the path difference. AP minus BP, when it is a whole number times a wavelength, we have the biggest oscillation, and I'm going to describe this by calling it a constructive interference. Constructive interference. So that would be, I'll call label it C. That would be this point here: constructive. Okay, but In between is where the path differences is a whole number, maybe plus half a wavelength. Okay, so in which case they would just cancel, the peak would just meet the trough. So I would describe this by calling it a destructive interference. So that will be the in-between points. So destructive, destructive, destructive. So there's no oscillation in the water surface here, and so on.